Hi, welcome back to Econometrics B. So now we're ready to our treatment of binary response unobserved effects models. So these are models where we have an unobserved effect. We call it CI. It's an unobserved effect that's individual specific and constant through time. Thereby, there's no index t on this variable. Okay, and we do not observe it, as opposed to xi, which would be like the entire sequence or history of explanatory variables at time t. So from time 1 up to capital T, the entire sequence. Okay. And so we are going to start to talk about how to estimate such models under strict exogeneity and also the index restriction. So again, we're interested in modeling the response probability for YIT equal to 1, that is that the binary outcome is equal to 1, conditional on the entire, in this case, in the entire history, both future and past and the current values of the explanatory variables, and then the unobserved effect. Now, the first assumption that we're going to make is the strict exogeneity assumption. What does that imply? What that implies is that once we have conditioned on the current value of the explanatory variables, we do not need to also condition on the past and the future, just as long as we also condition on CI. So the only persistence that's coming in those choices that are not explained by the explanatory variables is through CI. On top of that, we have the index restriction, that basically the response probability is a function, nonlinear function, that is usually has a domain between 0 and 1, and evaluated in a linear index. That's why we call it like an index model. Okay. The functional form for G, well, is assumed to be known, so we know the parametric form for this. If it's a probit, it's a CDF of a standard normal and can be motivated by the latent variable model, where you would have a latent variable that would be xit beta plus ci plus another random component that would be, say, epsilon it, that would be normally distributed. In this case, in this way, we can motivate the functional form for G as being the CDF of the standard normal through this linear index model. But for now, we're just going to work with the linear index and not worry about that epsilon that's kind of implicitly embedded inside G. Okay, so that's where that's kind of our model. Okay. Now, what does strict exogeneity imply? Well, strict exogeneity actually rule out a lot of things. For example, we cannot have lag-dependent variables or explanatory variables with feedback. The former, the lag-dependent variables, we're going to treat explicitly in the coming video on dynamic response, binary response models for panel data. There's another set of issues that arise there that would break with the strict exogeneity assumptions. We're going to try to deal with those. For example, the initial conditions problem. Variables with feedbacks, that's not allowed either. So, you know, if you think of, say, y being, say, the committing a crime, and x being whether or not you're spent time in jail at time t, if that is x, well, then maybe you think that if you commit a crime, that has potentially an effect on the future values of the explanatory variables, which would be whether you're in jail. So in other words, it could be feedback from present values of the outcome variables to future values of the explanatory variables. And so that would violate this strict exogeneity assumption. So we cannot have those kind of effects. So you think those kind of effects are in the context you're trying to model, well, then you have to try to explicitly model those feedback effects, or at least not use unobserved effects models under strict exogeneity. And so these reasons we've discussed those earlier. I'm sure that Jesper, he also talked about that in the context of the linear panel data models. Now, so this is kind of our model. So the problem is we can't really like just do appropriate with this CI inside, right? Because we don't observe it. Had we observed CI, well, we could just include it as another explanatory variable, and we could just run appropriate, and we'll be fine. Okay, together with the x's. The problem is that CI is not observed, so we cannot condition on it. So when writing up our likelihood, well, we have to write up a likelihood in terms of observables. So we can do conditional maximum likelihood for conditioning only on things we observe. Otherwise, it's pretty hard to calculate the likelihood if it suddenly depends on things you don't observe. Given that we are not observing it, well, we may actually either try to get rid of it, so try to see if we can make some smart transformation so that CI no longer appears in our model, or we might actually try to write up a model for CI. That could be that it's, for example, normally distributed, or it has some other distribution. The thing with the fixed effect or the differencing away approach is that it's not very easy, actually. I mean, you could see it would be easy in the linear probability model or in a linear model. We would just take first differences with you have the left hand side, you have y, and then you have xit beta plus ci, and then you just take first differences in time. And then since C is time constants not varying, it would be difference away. Or you could do the within transformation and take subtract individual specific averages. And then since CI is constant, it would also average out if you did that. We've seen that for linear panel data models. But here we have kind of a little bit of an obstruction. The problem is the G is preventing that type of transformation, so that's not even feasible. So we cannot do that. There are some certain examples where we can actually do it, and for example, for the Login model, we can make another trick that allows a transformation that removes CI, but it's really context like model by model specific. How you actually make that transformation makes it much harder to do fixed effects in nonlinear panel data models. Okay, so the first trick we could try to do is we could actually try to see if we could estimate CI as a parameter. So that's a possibility. It's appearing here. So why don't we just include a bunch of dummies, one for each cross-sectional unit, and then estimate that as a parameter jointly with the parameter beta that are coefficients to the explanatory variables. We've seen that was this, in some sense, a successful route in the context of the linear regression model. It's essentially equivalent to do a within transformation and do within transformation on the data so that you get the usual fixed effects model. So these two things, the within estimator or the least squares dummy variable methods, that can be shown to be equivalent. That's not the case here. Well, first of all, the first difference is that within transformation is not feasible because of the non-linearity of G. And second of all, it's not identical. Okay, so it's not. I mean, you can't compare it to something that's not even feasible. So why don't we just try to see if we can stick with the estimation of CI as a parameter? Well, there's some computational issues, right? That's the first one. So if you recall from the linear world, well, you would have to estimate coefficients to n different dummy variables in addition to the parameters you want to estimate already. So if you're running, in our example here, we have like 5,663 cross-sectional units. Well, you would have that many additional parameters to estimate. In the linear probability model, well, that would imply that the X prime X matrix would be, 5,000 by 5,000, or 5,663 by that number, or n by n. And that's actually a pretty small sample. So think about, working on the Danish register data, for example, where you have like, in principle, you could easily have data sets where there's like millions of observations, and a million parameters to estimate. That's pretty nasty. And it's getting worse, because it's not like a linear problem. We need to have use a maximization routine to maximize the likelihood function or minimize the negative of it, or searching over a parameter space that suddenly has, n parameters, or in the context of our 2 million different Danes example, 2 million parameters, okay? And that's really, really a big computational problem. And it's not, I mean, it's by no means easy to attack, okay? There may be lots of local minima, there may be, a lack of identification, and even if you were to, get it smoothly towards the maximum, you still have to compute variance, covariance, you still have to compute the Hessian matrix. Even if you have it in closed form, it's 2 million by 2 million to do your Newton's method. And of course, there exist solvers that are, like stochastic gradient descent and other algorithms that can deal with very high dimensional problems, but 2 million parameters, that's hard, okay? So I think, even just for computational reasons, in high dimensional problems like that, is not really something we want to try to work with. And then that's just the computational problems. On top of this, there is a serious identification problem, or or a consistency problem. It's really a consistency problem. It's called the incidental parameters problem. Now, if you recall from the linear regression models, we could still, even in the least square dummy variable methods estimator, we could still identify beta, even though we could not consistently estimate the unobserved effect. The reason why we cannot consistently estimate the unobserved effect is that as n go to infinity, so does the number of unobserved effects, okay, or the number of parameters to estimate. So it's not like you get more and more data per data point as you get, or per parameter as you get more observations. That's why you can't consistently estimate that parameter. Okay, now we're all fine in the linear world because we could just difference it away so it was not even there. Or we could just transform within transform, and it would not even be there, and you still could consistently estimate beta, even though you couldn't consistently estimate CI. So that's really a powerful thing about the linear models, but that doesn't hold in nonlinear models. Actually, the fact that you're not able to estimate the unobserved effect, or the parameters CI consistently, not only has an effect on our inability to estimate those, but also beta. So you cannot estimate beta unless you have very good precise estimates of all the unobserved effects, okay? Now, of course, we are considering in this book, really, in this course, we're considering the asymptotics that n is going to infinity, okay? That as we get more and more data, or we're considering consistency of estimators as we get more and more data in the cross-sectional dimension. If you were to get more and more data per individual so that t go to infinity, well, then you could potentially estimate CI consistently, okay? But you would need quite a lot of data points. Well, we have that in many cases, actually. And in the Danish register data, for example, we would be able to follow individuals for 30 years. So you could potentially get pretty good estimates in those cases, but still you have then the computational problem. So there will be some cases where it's potentially feasible to do it if you have very small dimension, cross-sectional dimension, and very high dimensional time dimension. Anyway, we're not gonna deal with this. In principle, this is just another application of the propet model. You just include a bunch of dummies. The other approach is a random effects approach. And here, since we're doing maximum likelihood and we want to describe the entire conditional distribution of yi conditional on xi, well, we need to also assume a distribution of ci conditional on the entire sequence of the explanatory variables and then integrate out ci. I'm going to show in detail how you actually do that. And we're going to draw upon some of the things we had in numerical methods in last year, about Gaussian Quadrature, or Monte Carlo simulation. So I'm gonna go more into detail with that in just a second. Here, the questions that arise immediately is what distribution should that be? And of course, it should be the distribution that we think has generated those CIs. But what distribution is that? A common choice could be the normal distribution, or some finite mixture. Or, but in principle, it's just as long as you can write up that distribution and integrate it out, well, you can formulate your model. So there's some degrees of freedom. I'm going to show you two examples of specifications that's been very popular in the literature. So here's some more possibilities. And like I said, it was not really super feasible to eliminate CI by transformation just from the outset, just looking at the equations we had in the beginning. So, it's not very clear how you make that transformation that makes CI disappear. And actually, it's not possible here because it depends on the functional form for G, whether that's even feasible. So we cannot differentiate it out due to the nonlinearity of G. And it's really not easy to find these transformations. I mean, this is if you find a transformation for the propet model where it's not even not exist from my point of view, well, let's publish and become world famous. It's existing for the logit model that has some where we exploit really the structure that is in the logit formula with the exponential. Once you start multiplying exponentials together, well, then what is inside the exponential is really just added. So there's some things here that really simplify when you work with the logit model, where you got an exponential over 1 plus an exponential. So that's, I'm going to show you the example below, and it's kind of more spelled out in the book than I'm going to take time to. And then you can do like a pooled analysis, and it's kind of, in principle, using the estimators that we've just covered in the previous video. So I'm going to spend most of the time on the random effects assumptions because, things becomes a little bit hairy. You may think it's a little bit, discouraging that what I'm going to end up finding is with this random effects model, it doesn't really matter that we are solving all these integrals. We could just, estimate the model, do a pooled analysis, and then we'll actually get the same parameters up to scale, and you'll just have to scale the parameters in some sense. Okay, but it's really the way forward to deal with the unobserved effects models for that are dynamic. So it's actually important to be able to deal with those. And then also, it's a good illustration of how you handle random components in econometric models. We're not only working with binary response models throughout our careers. So it's a simple example of that. Anyway, so here's a random effects linear index model. So we assume strict exogeneity. We assume independence conditional on CI and XI. So that essentially implies that once you're conditioned on the unobserved effect, and you have the strict strict exogeneity, what you can essentially just multiply all the densities or the probabilities for across the different time periods, because those time periods are independent. That's how you essentially calculate a joint density for say t different outcomes is if they're independent of those outcomes, conditional on x, I, and c, well, then you can just multiply all those probabilities together. Otherwise, you have to work with a sequence of conditional distributions that are multiplied together. But then what we are assuming here is that those conditions are kind of irrelevant and only captured by the current value of the explanatory variables. Okay, so that's why things are really simplifying. Anyway, there's a lot of hairy stuff going on here. The key thing is that those two assumptions are kind of implying that joint density for the sequence of observations of dependent variables from period 1 up to t. Okay, just multiply all the probabilities together. And that's kind of those that's independence assumption. Then you have normality, that the CI or the unobserved effect conditional on the sequence of observations. Well, that is normally distributed with a mean 0 and a constant variance. So it doesn't depend on x. Okay. Now this formulation, well, here it's actually a little bit, you can reformulate this, of course, but this current formulation, that implies that the unobserved effect CI and the entire sequence of explanatory variables is completely independent. Okay. Okay, so these are completely independent. It means that, when we, for example, we know that it's mean independent. So because the mean does not depend on x. Okay, so that's why we say it's mean independent. The variance is also independent, because CI conditional on xi does not depend on x. Okay, there's no, well, it's not heteroscedasticity, but there's no dependence in the variance of CI. Okay? And since the entire normal distribution is described only by those two moments, and nothing in that distribution is depending on x, there is complete independence between x and c. Okay, that's one assumption that's implied by that. And then of course we're also assuming the normality assumption. Now you can soften those assumptions, allow for some dependence. For example, it's very popular to let's say that the mean here, that distribution, be a function of xi, okay, or it could be, say, a function of the average of the explanatory variables. You could even let the variance depend on that too. Okay, so but the key thing is, in order to write up the likelihood, well, you need to specify what that distribution is, and if you specify a distribution that is not that is misspecified in the sense that it doesn't with a, at some set of parameters is equal to the true distribution, well, then you have a wrongly specified model. Okay. Whereas in the fixed effects approach, there's nothing about making assumptions about how C and X are related. So that is completely allowing for any type of dependence between the unobserved effect and the explanatory variables. And so we remember in the beginning, the first video here for binary response models, we did some regressions, OLS regression and the fixed effects regression, and we got very different estimates. I mean, these two estimators are consistent estimators of the average partial effects under the assumption that there's no correlation between the explanatory variables and the unobserved effects. So that's kind of, suggesting that there could be actually some dependence. So one thing we might want to do is doing like a correlated random effects approach, where we allow at least the means of the explanatory variables to enter into this mean. Well, we can look at that later. Okay, so that's a very that's one version of the model. Now, you can also, it doesn't have to be a normal distribution, it could be many other distributions, it doesn't have to be a continuous distribution, it could be a discrete distribution. So a very popular alternative to 3 is to assume some discrete support for CI and independence between the explanatory variables and unobserved effects. Okay, and actually I'm going to show that as an example because it's kind of, it becomes a little bit more intuitive. In a discrete example, it's kind of it's kind of straightforward to see what you are doing, right, when you're taking an expectation. So here's what is going on now. So here's we assume now that CI has a discrete distribution. Okay, so it can take only a finite number of values. So say it could be J here. Say it could take 5 different values somewhere. Take 5 different values with 5 different probabilities. Okay, that would be a discrete distribution, and we'll not be saying anything about where those values were. It could be, or we would not necessarily say anything about what those probabilities are, except that they need to be positive and sum to 1. So how do you calculate then the joint density? Well, we have the density, the joint density for the sequence of y, where we were conditioning on CI, which is no longer here. So this is what we have right here, right? This one we have fully specified that distribution, because essentially this here is just going to be G here times the indicator for y being equal to 1, and then plus 1 minus y times 1 minus g. Okay, so that's what f is, just as usual. Okay, now we can derive basically the joint density simply just by multiplying all the different time periods of those densities. Okay, or those like the contributions at the individual time periods. But these are all conditional on C. Okay, now what we're doing now is we can evaluate this density here conditional on C, right? We have a formula for that. And then what we do is we put in Cj, say 1 point of support, 1 point in the distribution for C, multiplied with that probability that is occurring. And then we just essentially calculating, say, the weighted average, or the probability weighted average of all those densities conditional on the different points of the port at C. Okay. And here you got your density here. You got that fully specified. We need to impose that those pi's, those probabilities, they're all summing to 1, and we may also want to impose that they're positive. Okay. Otherwise, it becomes a kind of funny distribution. Okay? And then another common restriction is to assume that it has mean 0. You can drop that assumption and then drop the constant inside this index here. So if you don't have a constant here, you will not need this restriction. But you can't have both. You can't both have a mean in the unobserved effect that's moving up, and then also a constant that can move down. And then you lose identification. Okay. It's like kind of like the dominant variable trap, or it's like we always assume that the mean of the error term is equal to 0, because if the mean was another parameter, you could just move the constant up and as you move down the mean of that variable. Okay. So here's an example with only 2 points of support. It's just it's the same as we had here. It's just spelled out with only 2 points of support. But you don't have to have only 2 points of support. You can kind of add more and more points of support, and then check if the parameters that you're estimating are significant. Okay, and then you stop eventually as they're becoming less significant. There's some issues about actually testing parameters at the boundary of parameter space, but let's not worry about that. Because probabilities, they can essentially not they cannot go below 0, right? And you cannot so that creates a little bit of some issues, because our theorems in chapter 12 and 13, they are kind of assuming that we're in the interior of the parameter space. That's kind of that's kind of that's not the main point here. Okay. Anyway, so so with two types of support, well, then there would be two support points, say C low and C high, for and then our joint distribution for yi conditional on xi, not on ci, but on in terms of observables, is the following. Okay, so it's probability that you are a low type. Well, that's two types, right? So a low type individual times the joint density for people who are the low type. And notice that this is constant throughout all time periods because it's individual specific, right? And then plus the other situation, 1 minus that probability for being a low type. That's the probability of being a low type. And this is, here we are embedding that restriction from the previous slide, that the probabilities need to sum to 1, times the density for an individual of type CH, so a high type. Okay, and now this here, that's CH, well, that's essentially just derived from this restriction here. You can kind of, write it out. It's like pi high times C high plus pi low times C low equals to 0, and then you move a little bit around, and then this is what you get for CI, or sorry, not CI, CH, or this guy up here. So you can like isolate that in this expression here. So so this is now conditional on something else, right? It's conditional on no longer on CI, but then on this CL. So what did we do? I mean, well, the nice thing now is that it makes more sense to estimate these parameters. Okay, we don't run into the same initial conditions problem, or it's not, we don't run into the incidental parameters problem where we would have that we cannot consistently estimate these parameters, because as the number of observations increase with n, well, then the number of support points is not increasing. It's actually fixed. You're assuming a fixed number of parameters and fixed number of probabilities and support points, irrespectively of how many data points that you have. Okay, so as n increase, well, you get more and more data to estimate each of these parameters, and then you have you can obtain a consistent estimator with maximum likelihood, and everything is fine. Okay, so here, of course, the point is that you're now using more observations, more individuals to identify those distributional parameters. And of course, if you have lots of observations, well, you can also estimate more parameters, but the asymptotics are clear. You let n go to infinity and you keep the number of parameters fixed. Okay, so that's for discrete support, and has been actually very popular, and is used to, it's kind of a very flexible way of having a distribution if you don't really know the functional form of it. Of course, it starts to become a little bit more hairy once you want to allow for the dependence with explanatory variables, like I kind of alluded to, you could do with the normal distributed version before, like this one. So let's return to this situation here where we assume normality. Okay. Now instead here of taking the expectation over a discrete distribution, now we need to take it over a continuous distribution. And that is, how do you do that? Well, then you take this function here, and then you integrate it over the distribution. So it's really the integral over the support of that distribution. So this is our function that depends on C. We need to integrate CI. We integrate over that distribution simply just by taking the density of CI, which is what we have here. Since it's a standard normal density, we have the standard normal density right here, where not the standard normal density. It's a normal density with sigma with standard deviation sigma c. So this is the density for a normally distributed variable with that standard deviation. Okay, and this guy here is the standard normal density of the standard normal distribution. And so then we are basically when we're taking an expectation of a function of a random variable, well, then it's really the integral of that function of that random variable times the density and then integrated over its support, which in the case of normal distribution is from minus infinity to plus infinity. So this is how you calculate expectation, right? You integrate that out. And now we have, again, density or joint distribution in terms of observables only, because we integrated out that CI, okay? So, and again, here we have that density, which is really, that which is really the, you know, what is, yeah, it's really, you know, the usual guy where you get from binary response models, right? There's these two different outcomes that are feasible, and then you wait with the observation that that's the case. Okay, so now the next question is, once we have written up what it is our joint density is, right? Well, well, we still need to evaluate that at the data points for YIT, and then we need to take essentially the logs and then maximize, and then, you know, we're done. But we need to, before we can go so far, we need to be able to solve that integral. And so we have seen how to do that in previous courses, like numerical methods. And one of the two things we have in our toolbox so far is Gaussian Quadrature and Monte Carlo simulation. Okay, I'm going to mostly focus on Gaussian Quadrature in this case here, because it's a fairly small dimensional integral. It's actually a one-dimensional integral, and we really learned from our course in numerical methods that you know, Gaussian Quadrature is very, very precise in one-dimensional problems, or in smaller dimensional problems, but has this cursor dimensionality built in. Whereas Monte Carlo simulation really breaks the cursor dimensionality, but then has, you know, some finite sample issues that makes Gaussian Quadrature more appealing in smaller samples. Okay, so we're going to use Gaussian Quadrature. Now here, there's a choice of quadrature method, and actually, the most straightforward choice here is actually Gaussian Hermit quadrature. But you could also use Gauss, the gender quadrature, after some transformation of this problem. I'm going to show you just a little bit of a recap before we move on Gaussian quadrature, in case you forgot what happened before Crispus. So really, we have an integral that has this form here. So there is some function we want to take a integral over, and then there's some weighting function W that sometimes can just be 1, right? Like then you would have a Gauss-Legendre, and you integrate that from A to B. Okay, and A and B can have, you know, it can be either a finite support or it can be an infinite support, depending on the quadrature method. Now this is the integral of interest. So and we should be able to with quadrature to rewrite that as a finite sum of quadrature weights times the function evaluated and some quadrature nodes. Okay, and then some plus an approximation error. Okay, it's not exact, it's an approximation error, but as the number of quadrature nodes increase, well, then the approximation error is going to be very small, and you know, basically the nodes and weights are chosen so that there is no approximation error if the function f here belongs to a family of 2n-1 degree polynomials. Okay, and as we know, we can approximate, you know, smooth functions with polynomials arbitrarily close as we get very as we increase the number of the degree of the polynomial. Okay, and the normal distribution is a fairly smooth distribution, and this our function is also a fairly smooth object, so it should be not too hard to approximate this with quadrature methods. And here the choice of method differ by weighting function and the domain, and here's some popular choices. You have Gauss-Legendre. We used that for our portfolio choice model last semester. You have that's the simplest one, and the one I'm actually implementing in the code in just a second. it has a weighting function of 1, so you don't have to worry about that weighting function, and then it has a finite domain. Now our integral is actually a little different here because it has infinite support, and it has it has yeah, well, there's not necessarily a weighting function that just determine what the function f is, right? So but it has infinite support, right? And actually the best choice for solving our integral is not really Gauss-Legendre quadrature. I'm doing it just for simplicity. It's going to be Gauss-Hermit quadrature. And why? Because we have at the end of that integral here that we're trying to solve, here, inside here, it says something, it's proportional to something with the exponential to the power of minus z squared, okay? Like, that's going to be clear. And has a domain that is infinite, minus infinity, plus infinity, since the CI is normally distributed with a full support on the entire real axis. So that's the two potential choices we're choosing between. This would be, say, less appropriate, Gauss-Chebyshev here, and Gauss-Legendre quadrature. That's also less appropriate. It would be good for actually if you have a log normal distribution. It would probably be better because then you have like a finite support in the low end, and then you have a infinite support in the upper end, so like from A to plus infinity. But we have normal distribution, so we're going to look at Gauss-Hermit and Gauss-Legendre. So I'm going to start with Gauss-Legendre quadrature first. So here's just, you know, a little bit of repetition of the formula. So these are you know, in the pure form, it's made for integrals on you know, the interval from -1 to 1. And then you can rewrite that as a finite sum of weighted function values evaluated at the nodes. Okay, you get the nodes from Python. They can be computed, or sometimes they're actually pre-tabulated. It's much faster. So these are good for essentially computing expectations of random variables with finite support, like say from -a to +a, because, you know, this is an integral that has a finite support. You can easily make a change of variable that so it goes from a to b instead of, you know, a general integral instead of just -1 to 1. And it can also be used for computing expectations if we're making a transformation using the inverse CDF, so that the domain becomes 0 and 1. Like, you know, we have a normal distributed variable, but if we take the inverse of that normal inverse CDF of the normal distribution for that normally distributed variable, well, then you get something that is a probability, which is a uniform distributed variable suddenly. Okay, so then it has the domain between 0 and 1. Okay, so this is the trick that we're going to use. The method of choice is, you know, this is really the method of choice. No obvious weighting function can be used. Here for me, it's a method of choice because it's a little bit easier, not having to deal with the weighting function. I'm going to talk about how to do it with Gauss-Hermit. Is not that much more difficult. It's just a little bit more easier with Gauss-Legendre. Anyway, you can do a linear change of variable, basically to transform the interval from -1 to 1 to be on A to B rather than -1 to 1, and really just instead of simply just making a change of variable. And that can be done in this very simple way. So essentially, you start with your quadrature nodes x, and then no, you start with you start with your quadrature nodes x, and then you just make this transformation, and then you get basically mapped into the -1 to 1 interval. Okay, so by making this transformation, so that should be doable. I think we also covered that last year. So with all that repetition in place, let's go for it. Okay, so we can reformulate the integral by making this simple change of variable. So we recalled that CI was normally distributed. So how do you get a normally distributed variable? Well, you can take a uniformly distributed variable and then put inside the inverse CDF of a standard normal. Then you get a standard normally distributed variable. Then you multiply with its standard deviation, and then it becomes normally distributed with that standard deviation. So this is, if this is normally distributed, uniformly distributed, this is normally distributed with this standard deviation. Okay, so that should be no. Okay. So now we essentially just replacing this here inside with our transform variable, and now C is no longer appearing, and we want to take expectation with respect to Q instead. But now Q is uniformly distributed, so we take basically integrate over the uniform distribution, which just has basically a constant density. And so since that density integrates to 1, well, everything is beautiful, and we end up with this very simple integral. Okay, and what is this? This is exactly in the form we wanted for Gauss Legendre, right? You got a function here of a of some random variable that is integrated on a bounded interval, from 0 to 1. Okay, so this is our A to B interval. Okay, and then you basically take this function here and approximate that with Gauss Legendre quadrature. So you can rewrite this simply as a sum, a weighted sum of those function values evaluated at the quadrature nodes. Okay, so now Q is quadrature nodes, and these are the quadrature weights. So this is essentially the form, just like we had before, right? Now, of course, these weights I'm using here on the next slide is already weighted to be on the interval. Okay, so these are adjusted to be on that interval A to B, or minus or 0 to 1. Okay, so A is 0 and B is 1. And here's how you actually do that. Okay, for our implementation of the random effects model. So here, everything is the same as before. This is like the objective function for the random effects model. You may want to switch back to the previous video when I went for the pull propet model. Here it's the same thing. We do a little bit of work, to parse the parameters. I mean, before there was only one set of parameters, the betas, but now we have an additional parameter. Okay, we have sigma A. Okay, so we're going to put that in the last element of the parameter vector. So first you have all the betas, and then in the end you have the sigma A, or the sigma C in the notation on the slides. Okay, so we have these two sets of parameters. So if you have k exponential variables, we have k plus 1 parameters testing. Now then we do the usual stuff. We do the x beta, evaluate stuff here. This is not necessary for calculating our likelihood, so don't worry about this. Okay, but then we need to calculate our joint density. Okay, so here's what I do. Here first I calculate. There's another function that's doing the quadrature nodes and weights adjusted to the interval A to B. And actually we can go and look at how that transformation was done. So I think it's where is that? Do I have it somewhere here? Yeah, here it is, the function. And here this is the simple transformation on that interval. So you basically take the nodes that fits on the interval 0 to minus 1 to 1, and then you make those adjustments implied on the slides, and then you get new weights that are adjusted to that interval. Okay, so that's just out of the box. Then once you got your weights, I do a little bit of reshaping because I want them to be like 1 by R. The number R is the number of nodes. Because then when I multiply with other things, it's just going to broadcast nicely. So I have always the quadrature nodes in the columns. Okay. Then I calculate eta, which is basically it's the quadrature nodes evaluated at the CDF of the standard normal. Okay, so if this was a simulation of uniform random numbers, these would be standard normally distributed numbers once they pass through the inverse of the CDF. So this is what we essentially saw here, right here. This is what I'm calculating now. Okay, and then essentially to get C, I need to multiply with the standard deviation of it. Okay, so we move further down. I call this is the next line, right? I multiply with the standard deviation, and here, sorry for the confusion notation, it's called sigma A and not sigma C. Okay, and then what I do here is I evaluate the density at x beta plus alpha. Okay, so this is what we have here. This is our formula for this guy here. Let's go a little bit back and see if we can actually find the formula here in the slides. Well, that was what we had right here. Does it match with what we have let's actually find the code here over here in the right place. It's the same, it's identical, just copied in for convenience. Well, where do we have it? Well, this is a probability evaluated at x beta plus C. Okay, and then we calculate our density for y with these two different outcomes. This is exactly this formula here. Okay, so we're just doing step by steps. Let's move back and see in here where we were. Where was the product here? So this guy here. Now we know how to calculate this. We know how to calculate this guy. Then we just take the product of all the time periods. That's the next thing here that's going on down here. Where's the product? I'm taking the product over all the time periods. And then what I'm doing here is I'm taking essentially the sum, the weighted sum over all the quadrature points. That's what's going on right here. Okay, so we're taking the weighted sum of this product that we already calculated, and then we're done. Okay. That's our estimate for the joint density. We're not entirely done because we want to do maximum likelihood. So we are also doing what we are taking the log of that density in terms of the observables, and then we are taking the log. We're taking the log of that, and then the negative value, because we're minimizing the average log, negative of average log likelihood. And that's what we throw at our solver after taking the mean over all the observations. Okay, it's kind of there's a lot of stuff going on here, right? But I think you can do it. I mean, go forth and back between the code and the equation. See if you can you make the things add up, and it's not that hard. Print things out, see what the dimensions are. Does it make sense? Okay. Anyway, I really love it. I think it's fun. Okay, so anyway, so let's move on. Let's party with some Gaussian Hermit quadrature. Okay, that's actually really what you want to do, and would be the standard thing to do for solving random effects models, because it's utilizing the special structure that the standard normal density is. That it has the weight, it's kind of proportional to the weight that is in this integral. Okay, so we are solving integrals that has on this form. Anyone that remembers the standard normal distribution well would remember that it actually is looking like this. Okay, so this is part of that density, and then you got the rest of the density out here. So I can just move that constant outside the integral. And so here you got a mean of a standard, a mean of a normally distributed random variable y. So and then you take a function of that. So if you want to calculate the expectation of a function of a randomly normally distributed variable y with standard deviation sigma and mean mu, it's going to have this expression. Okay. Just like we did before. Now you can, with a relatively simple change of variable, again, make it reformulate it so that it's no longer a function of y, but a function of x. And sorry for this abusive notation again. Y and x is not the endogenous and explanatory variables. These are just, you know, generic variables that we are using only for studying quadrature. Okay, so don't get confused with our usual y's and x's. Okay. Anyway, after this change of variable, you can define x such that y that is equal to y minus the mean divided by the square root of 2 times the standard deviation. Okay, so that we got y is equal to the square root of 2 times the standard deviation times x plus mu. Okay, and then you differentiate this guy here with respect to x, and then you get essentially square root of 2 times sigma. Okay, and then you move the dx to the other side. Okay, so you know here dy that's you can derive directly from this. Now, then we just essentially replace all this stuff up here, and then we end up with this simple formula. Now, so what do you have? You have the pi to the power of minus 1/2. Okay, so 1 over the square root of pi times this integral here, which is some function here, some function of a random variable x. There's a random variable x, or a variable x. That we want to integrate over from minus infinity to plus infinity times e to the power of minus x squared. And this is exactly the integrals we have in mind. It's functions of x times the exponential of minus x squared dx. Okay, so this is exactly an integral in this form. So all we got to do is essentially basically approximate this with quadrature. So we got function values at the quadrature points times the weights, and then sums of all the different elements. That's essentially what we're doing. So let's do it for our model. So approximating the joint distribution of yit or yi conditional on xi using Gaussian Hermit quadrature. So here's the integral that we have to begin with, right? And then really, this is a mean of a normally distributed variable, or a function of a normally distributed variable c that has a standard deviation of sigma c and a mean mu of 0. So in the context of this notation over here, mu would be 0 here. And then, well, we just take this function here. And then evaluate it at what was inside here, square root of 2 times sigma times x. Okay. Now we put that right in there. Well, I call it set now. Sorry again. So x from previous slide is now set, and the guy we're integrating over, and then times the exponential of minus x to the power of 2. Okay, now beautiful, right? Now we're back in business. We have essentially a function here that is multiplied with this weighting function minus set squared in the exponential, and then integrated from minus infinity to plus infinity, and then we got integral on this form. And this is exactly what Gauss-Hermit is meant to deal with. Exactly this, and we can approximate it by as basically a weighted sum of this function evaluated at the quadrature points. And those quadrature points, those weights, are things we can just, compute once and for all. Okay, and we get those, and there's a Python function for that as well. You can also compute them yourself. That takes a little bit of time, but these are the weights and nodes, and again, the more nodes, the more precise this gets. And then I've just put back in the function, so you got your entire expression. I've not implemented this in the code, but it's actually a nice exercise. Try to see if you can make Gaussian Hermit quadrature work instead of Gaussian general quadrature in the context. Now I'm going to just quickly say how would you do this with Monte Carlo simulation. Well, the simulation simulated likelihood contribution for individual I would obtain in the following way. Okay, so what you would do here, I mean, this is in This is something you do instead of doing quadrature, okay? So it's another way to approximate the integral. And see, the logic here is really, if you look at this integral, what is this? It's a mean of a function of a of a stochastic random variable. Okay, what do we do? How do we approximate means? Well, we use the analogy principle, right? This is how we've been approximating means throughout this course, right? You know, you approximate, you take the sample average, and you approximate the mean with the sample average. And you know, as the number of observations go to infinity, well, then the sample average is going to converge to that mean by the law of large numbers. Okay, exactly the same logic we're using here for Monte Carlo. Okay, so we take and see, how do we get the sample? Well, it's not really a data sample. The nice thing is, you know, its distribution, so you can simulate a sample. So you can just use your computer to simulate a sample from the distribution of C, and then just average the results. That's basically the logic here. So what you do is you take, again, R independent draws from the standard normal distribution. You label them eta. Okay, so and then you scale them up so that they have the right variance. So now they are normally distributed with the variance sigma C. Okay, and then, well, again, you compute the joint density conditional on that value of C, just like we did with the quadrature points. Okay, and then you just average the results and take logs. Okay, and then you got essentially your simulated likelihood function. Okay, now here all we've done is we have taken the integral that appeared here and replaced with a sample average. Okay, a sample sum. Okay, so we're taking the mean and replaced with an average. Okay, you can do that as well. Okay, and so this is very powerful. And then estimation would be, it's called the method of simulated likelihood. It's maximizing the sample average of the log of the simulated likelihood. Okay, so this is the likelihood contribution for individual I, and then you need to average all the results. It's kind of important to get the log in the right place. Okay, so don't take the log outside here. That would not be correct. And don't put the log inside here and think you can rule out that product. That's that pretending, because, you know, logs of products become sums, but that's not correct. So this is the way you do it. Again, you have to, just like you would do before with the quadrature, you would estimate, you would maximize this simulated likelihood with respect to two parameters, beta and sigma c. Okay, or you could have sigma c squared. It's actually easier to work with sigma c as being the parameter, because then you're sure that the variance is always positive. Even if you get a negative sigma c, well, then this implies a positive variance, right? Because, you know, the variance of this random variable is going to be sigma c squared, and then the minus disappeared. Okay, just a few remarks before we continue with discrete choices on simulation-based estimation. So here's some few words about the properties of this. If R is fixed, maximum simulated likelihood is actually inconsistent. We're going to talk more about that later. But why is it inconsistent? Well, it's because we got an approximation error in the likelihood function. Okay, and you can, in some sense, say that's also the case with our approximation with integrals, right? Because if the approximation is not completely accurate, well, you don't have approximated the likelihood correctly. Okay, so there's still going to be errors. Okay, but here, once we start talking about the number of draws being a stochastic variable and study the asymptotic consequences, then when we say here, when R is fixed and method of simulated likelihood being inconsistent, it's still because we are talking about what's going on when n go to infinity. Okay, so if R is not changing as n go to infinity, well, that approximation does not become better and better. Okay, and actually, here the problem actually arises because of the log here. So you're taking the log of that those probabilities, and that's a nonlinear transformation. So whatever simulation noise that would be of the density in here would not be simulation noise, but simulation bias. If R is increasing, but it's increasing smaller than a rate of root n, the estimator is consistent, okay? Just as long as it's increasing, as the number of observations increase. You know, a more pragmatic way to say it is you just need to have R increase as well in order to get consistency, because otherwise, well, there's still going to be some bias left in the approximation of the integral. If it increases faster than root n, well, it's equivalent to maximum likelihood. It's asymptotic normally efficient and completely equivalent to maximum likelihood asymptotically. So, and that's kind of clear, because then that whatever simulation noise that would disappear faster than the sampling error that would come because you have a finite sample of observations of, you know, y's and x's. Okay, this was a little bit, you know, hairy. I think you will live without all deep insights, and it should totally fine during this course. So, but I think, you know, I just wanted to mention this, given that we spent time on it last semester. So, well, I think I kind of talked a little bit about how do you, so back to the model again, how do you relax the assumption on the unobserved effect with the random effects framework? Remember that we're assuming that it's uncorrelated with that the unobserved CI is uncorrelated with the explanatory variables, because we assume that CI has mean zero conditional on X. Well, like I alluded to, you could just do this Chamberlain approach. You specify the correlation, put inside that mean a function of X, put inside the variance a function of X. Okay, so that's doable. We're going to do it. Serial correlation, we are assuming that no serial correlation in the remaining observables. If you think in terms of the latent variable model, the last error term that is normally distributed, well, that is not really, we're assuming it's serially uncorrelated, right? That was the independence assumption that led to our joint distribution. Let's go back and see if we can find it. Okay, it's quite some way back. Well, maybe I can't find it. Well, it was right here, that conditional independence assumption. Okay, let's and that other thing I was talking about the mean independence in independence with X. That's this assumption here. Right? Let's go back. Yeah, we are almost there. Okay, so but you can actually specify. You can actually allow for correlation. Now, this would require not a one-dimensional integral to integrate out that entire distribution of another random variable to allow for any arbitrary correlation across time. It would be a t-dimensional integral. Okay, like you know, just recall from our portfolio choice model last semester, we had like a portfolio of different choice of different assets that were all potentially correlated. Well, here it could be the same, right? It's just observations of the error terms at different time periods, t-dimensional integral. Now, in those cases, simulation-based estimation would be very powerful. It's way beyond the realm of this course, okay? I'm just saying that simulation-based estimation really has room for estimation of models with many random variables, and it does exist, and you can eventually do it as you you know, study some more econometrics. That was a random effects model, or many different approaches to random effects models. Here is a few words, just briefly, on the fixed effects transformation. The trick is the following. So what you do, well, recall that we could not just do the transformation like a first difference and make CI disappear from the equation. We have to do something else, okay? It turns out that it's actually feasible in the context of a logit model. So what we do is that we model the joint distribution of yi not only conditional on xi and c, like we've done all the time. Like, remember I mean, you got that distribution right here. That's what we've been trying to work out all the time, right? Where we have conditioned only on X and C, right? Now, instead of that, we also condition on another variable, N, Ni. What is Ni? Ni is the sum of YIT over all the observations, okay? Over all the time series observations, okay? So it's a number of times where we have observed a success, or Y equal to 1, for individual number I, okay? And so we also going to condition on that. Well, this is observable in the data, right? So now we can if we can derive that distribution conditional on xi, ci, and ni, well, we just added another observable. Well, the trick here is that once you condition on both xi and ni, ci disappears magically, okay? After some transformation, it just disappears, okay? I'm not going to go through the entire math. There's actually some more equations that spells it more out in the book, but I think it's instructive. You just have to trust me that it works just to show it for the time period t. Now, for time period t equal for an observation where we have 2 time periods, okay, the simplest possible case. Now, in this case, well, here is the probability of yi2 being equal to 1, conditional on xi, ci, and ni equal to 1. Okay? Now, in this case, there is only really 2 possible interesting outcomes here, right? When we're looking at t equal to 1, that's where it's either y2 at time period 2 that's equal to 1, or in time period 1 that is equal to 1, right? Because n is equal to 1. So it has to be either in one period or in the other period, okay? Now you can derive it could be shown that that probability for y2 being equal to 1, conditional on n being equal to 1, well, that's a logit formula. This is a logit formula. So the exponential of whatever is inside divided by 1 plus that exponential of whatever is inside. So that's a logit formula here. So it can be shown that it's a logit formula evaluating the difference, the time series difference between the 2 time periods times beta. And now the magic here is there is no CI, okay? It's not there. And actually, you can sit down, work out those distributions. You have to work with conditional distributions, and there's some more hints in the book. But then, because all these exponentials, once you start to multiply exponentials together or divide them with each other, then it's really just what is inside becomes additive, right? So if you take the exponential of x1 times the exponential of x2, well, that's the exponential of x1 plus x2, and this is why you suddenly get that linearity from all those multiplications of what is inside, and through that linearity you can move the CI. That's very, very cool, a very cool insight. Okay. Okay, so anyway, so that's for the one outcome. Then you got for the other outcome, okay? 1 minus that probably. This is for the case of t equal to 2, and of course you can generalize this idea for t equal to 3, 4, 5. It's just it's many more combinations, and you would have to write a little algorithm that trace out all those combinations. But it's really, in some sense, it's really just mechanics, okay? So how do you get the likelihood contributions? Well, for here's your binary indicator that n is equal to 1. And then this is basically what is this? I'm blanking on that now. That's Isn't that? I'm blanking on that. I have to look that up. I just I should know. I totally blanking on it. So let me just think. It's getting a little bit late. Let me think. Okay. It's an indicator for making that transition, of course. Okay, so this is an indicator for first not observe, first having in first period having y equal to 0, and then the other period y equal to 1. Okay, and then you've got the other example here. Okay, so because it has to match up with those probabilities. Okay, so yeah, sorry for that confusion. That's a lot of stuff, you know, to remember. And then of course the generalization of this, well, that would have other indicators for the relevant sequences of choices that you're modeling and you're deriving the probabilities for. And that's in Woolridge's textbook on page 622. You got the likelihood contribution for the general case. I'm not going to go through that. Okay. Um, okay. So the things that are actually quite important to understand with the fixed effects regression here is that it has severe consequences for identification. Well, we are imposing less structure. We are being completely agnostic about the distribution of CI. No assumptions about that. It's gone, right? But this means that the things we are usually able to identify into binary response models are no longer identified. We still, I mean, we still have the scaling identification problem we talked about last time, but it's way beyond this. Okay, so the problem is that the condition. Well, first of all, you cannot identify the partial effects. The partial effects are not identified. So that was the case before, right? We could identify the partial effects even with in the random effects logit model and also in the probit models. We could identify the partial effects. Okay. That's not the case here. Okay. See, the conditional distribution of yi is not informative about. That's another thing. Similar to the linear regression models, if you don't have any variation, time series variation in YIT, well, you would not have any information about beta. With n equal to 0, if nobody is making any changes, if y is not varying at all, well, then once you condition on n, you perfectly predict the outcomes, right? If you assume n is equal to 0, well, then if you condition on n is equal to 0, well, then you for sure know that all the y's are equal to 0. If you condition on n is equal to t, well, then you for sure know that y1 plus y2 plus y3 all the way up to each of those y's are equal to 1. Okay, otherwise it would not give t if you have t elements. Okay? So this would perfectly predict y. Okay. So in our example with t equal to 2, well, n equal to 0 and n equal to 2 would perfectly predict yit. More generally, it would be with n equal to 0 and n equal to t. Okay, and this is also why we don't even need to write up the basically that in the likelihood. They're just disappearing. Okay, you could say in some sense. Yeah, they're just just disappearing. The likelihood or the probability is essentially 1. You take the log and then you get 0, right? So it's not going to be the likelihood. Then what can we identify? Well, we cannot identify beta. We can identify beta up to scale, just like before. But what is it good for? What is it good for to have the identified beta up to scale if you do not know what the distribution of the unobserved effect is? Okay, well, maybe you know that it has mean zero, but if you're willing to assume that, but if you don't know that distribution, how can you even start thinking about calculating partial effects? Well, you could calculate, potentially try to see if you calculate partial effects for an assumption about what C is, but what would that be, and how is that correlated with the explanatory variables? The whole point was that not assume any correlation with those explanatory variables. So you cannot get the average partial effects, so we don't have the distribution of C. We're not willing to make that assumption. That was the whole point of doing fixed effects. And the partial effects cannot be estimated unless we assume a value of what C is. Okay. What we can identify is the partial effects of the log odds ratio. If you calculate the log odds ratio, it's going to be x beta plus C. Now that depends on C, but if you take the partial effect of that, differentiate, well, then what you get is beta. Okay. So this is mostly useful really for, determining the sign or direction of effects. And the problem is you can't really get the partial effect, which tells you about the magnitude. But for testing, that's a brilliant choice. Now, that was a lot of estimation. Okay, so let's try to do a little bit of simulation. Okay, let's try to use these models that I implemented in the Python code and see if we can, use those estimators to estimate parameters based on some simulated data. See, the idea here is we know what's going on. We know what the data generating process is. So let's use this as a test bed to see if the different estimators are capable of identifying the parameters of interest. So here we got basically a model, which is a latent variable model, where we have some time varying explanatory variables. We have a lag dependent variable. We're going to put that row to 0 for now and just work on, be patient. We're going to talk about dynamic models later. And then we have our unobserved effect. We have an epsilon IT or EIT here. And we assume that is IID normally distributed, no correlation with the explanatory variables, completely IID, no serial correlation, anything. It's just, random draws from the normal distribution. And then we have our unobserved effect, CI, which is allowed to be correlated with the first observation of YI. We're going to put those coefficients here to 0, okay? Okay, we're going to put this coefficient here. This is just a constant. You substitute that in, you got a constant in the model too. And then you got AI. This is why it's called AI before, or alpha I. That is assumed to be normally distributed. This guy here is really identical to our random effects model, which is specified earlier. If we put rho equal to 0 and we put this phi here equal to 0, okay? So we're gonna try to see if we can simulate some data from this model. Okay, and there's the code for looking at it is inside this index models. So where is that? It's the simulate, and you can see here in some sense it's really just a repetition of the equations that you see in the slide. A little bit of context here. First, it's really important that you simulate the exogenous variable. So constant is exogenous. Set IT is exogenous. We assume it's normally distributed. The initial conditions, well, we assume that is exogenous. Okay, so it's not necessarily correlated with anything. It could be correlated with explanatory variables, but we assume it's just exogenous. And then we calculate the unobserved effect CI as a function of those, just like we had on the slide, right? So this is this equation here, okay? And then this last part here, well, that's the alpha I, right? So it's a normally distributed variable with variance sigma A squared, okay? That's this guy here at the end that has this distribution, okay? Now we are kind of ready to move on and do the dynamics. And if you are not doing any dynamics, essentially you would just say x beta x delta plus ci plus epsilon, and then evaluate whether that's positive. We are doing dynamics, so that's why we are doing the simulation in a kind of a recursive way. We first start with observation number 1, time period 1, then you do it for time period 2, time period 3, and so on and so forth. Okay, but you can look at the simulation module yourself. Okay, so this is I've simulated some data here with rho equal to 1 and delta equal to 1. Okay, and then let's try to see if we can estimate that delta parameter and that sigma parameter. Okay, so we're gonna do a bunch of experiments. So first, we're gonna do an experiment where we have no heterogeneity. Okay. And then we will want to see if the linear probability model gives a good approximation to the average partial effect. Well, we kind of already seen that, right? But now we know what the average partial effects are. And does the Pohl-Probert estimate the true parameters up to scale, like beta? Does it estimate those parameters? We know that our parameters, or it's called delta, the coefficient we're looking for, that's supposed to be equal to 1, because that was the case when we generated the data. So that's the first experiment we want to do. Okay, so let's try to do that. So what I did was here I simulated 1,000 observations, or 1,000 individuals with in t time periods, and we estimate, we assume that the error term for the lag dependent variable is normally distributed. And then we have the delta parameters. You can also assume it's logistic distributed, then to get the logit simulation from a logit. Then you have delta equal to 1 and sigma equal to 0. The rest is essentially just 0. Okay. Then we estimate the model with OLS. Okay, so this is our linear panel data model, where we use pooled OLS. We do a linear panel data model with fixed effects. Okay, so this is the one we're doing, and then we are doing a pooled probit. Okay, pooled probit. Let's see how that goes. So here's the results. See, the pooled OLS regression on these simulated data, there's no correlation between unobserved effects and explanatory variables, predicts a coefficient on C, our time varying variable, to be 0.22. Now that's of course a linear probability model, so it's not going to estimate that delta. Okay, but it may actually estimate the average partial effect. Let's see how it's affected by the fixed effects regression. Well, you get approximately the same. Standard errors are similar. We get the same, essentially the same estimate. Okay. And that's not so surprising, because Pohl-Probert and a fixed effects regression is both consistent for estimating the same parameter if there's no correlation with the explanatory variables. So that's kind of reassuring. And then look at this. This is the average partial effect that you estimate from the Pohl-Probert. That's very close to those linear probability models. And what about the Pohl-Probert? Well, that parameter is supposed to be 1. So what is going on here? What is going on? I mean, maybe it's the heterogeneity. It's because we had the unobserved effect. Why don't we try to see what happens if we don't have it? Do we nail it there? There we really nail it, right? So we got the average partial effects. Well, again, they match all the way down. They're identical across the different models. And actually, these are the average partial effects. They're close to the true ones. You can calculate them analytically. They would match up with this. So, but once we have a little bit of heterogeneity, unobserved heterogeneity, that variance of that unobserved effect increases, well, then our parameter decreases. So what is going on? Well, recall that we only estimate parameters up to a scale. Okay, so when the variance of the error, we're here that scale would be sigma, and sigma would be the variance of the error component in the latent variable formulation. Okay. To obtain identification for probit, what we do is we normalize that sigma squared to 1. Okay. So let's go back and look at what was the error component. Well, it's Ci plus epsilon I, and this guy, it's only this guy that has variance 1. This one has another variance. It has a variance of sigma A. So the joint variance here is really, you know, it's really 1 plus sigma A squared. Okay, so the standard deviation is the square root of that. And that's definitely not 1, right? And yet we're making normalization, assuming that variance is 1 in order to obtain identification. So we do that to obtain identification so that, you know, it's not completely in line with the estimated model. So it's not surprising that we get parameters that are smaller and smaller and smaller, okay? Because we have these two errors and the joint variance is this. So what we have really estimated is not beta divided by, is not beta or the, you know, the delta parameter we're looking for, right? One of the coefficients. It's that parameter divided by the joint variance, which is not 1, no longer 1, right? This is why as we increase the variance, these parameter estimates going to be smaller and smaller and smaller. And then the issue is we don't really actually can do much about that because it's generically unidentified, that scale. And actually, unfortunately, it doesn't matter for our for what we are really interested in estimating. We're interested in estimating, say, the response probabilities, right? Which is exactly what we get, right? This would be actually, now I'm neglecting the unobserved effect here. So this would be actually for an unobserved effect, assuming C is equal to 0, okay, for that particular guy. So this is not really the object of interest, but this is what we're consistently estimating. And then, but then the average partial effect, well, that is actually this guy here, right? So here we should, if you put plus C in here and plus C in here and, you know, take the derivative, right? You're going to get this, okay? Where with this C here, sigma here is actually equal to this term here. And it turns out that once you average over that component C, you got the average partial effect, average over the distribution of the unobserved effects, which is usually what we want, okay? So this is pretty nice, actually. The pool probit is well, you can then ask, is neglected really a problem in static models? Well, it doesn't appear to be the case, okay? And also, you look at the average partial effects, well, they're not, well, of course they're going to be affected by adding a lot of unobserved heterogeneity, but that's a real thing, okay? It's because it's a lot of heterogeneity, a lot of different people, and there's some people who are so far away from being on the margin of changing their choice because they have this huge value of CI, okay? Nobody, how much you change X, there's going to be a 0 effect, okay? There's going to be a lot of those if there's a high variance, and a lot of those with a very low values of CI when there's a low variance, okay? So increasing the amount of heterogeneity will in this simulated sample will, you know, structurally not only just estimate it, change those average partial effects. Also, if you calculate them theoretically. Okay. But given that they have this number, we are consistently estimating those. That's pretty nice, actually, with a pull probe. Okay, now let's return to the next question we had on the plan. Does pull neglected this is a, should we use pull probe or LPM? I think this is not really, this is not a little bit out of places. What I wanted to analyze next is, in case we have heterogeneity, does a pull probe actually estimate the true parameters if we are neglecting that heterogeneity? Okay, that's actually what we just looked at. Okay, so before we first looked at this, in the case there's no heterogeneity, no neglecting of the heterogeneity, does the pull probe estimate the true parameters? Well, yes, they do. Okay, in the neglected heterogeneity case, well, we added the sigma and just estimated pull probe. Well, it didn't actually estimate true parameters, but it did estimate them up to scale. And let's actually try to see if that happened, right? Because if we take those parameters we just estimated right here, okay, those parameters right down here, and scale them down by that estimate, that true true parameter here, simply, or multiply them, calculate that scale parameter. Does we actually, does it compare to what we estimated? So remember the number here, it's like 0.43. Well, the true delta was that. Okay, so here's a different alpha, so we need to do it again. Yeah, okay, so another simulation, another number. So it's theta has 0.45, and then if we simply see the true delta here was assumed to be 1. Okay, I printed that here, but in the pull probe we got 0.45. But if we were to divide with 1 times the square root of 1 plus sigma alpha, we get a number that's very close. And actually, why don't we try to increase the number of observations, say 10,000 observations or in 10 time periods, and you see it's completely nails it. Okay, so so that's for sure. The pull probe is nailing the parameters up to scale. Okay, and in that sense, neglected heterogeneity doesn't mean a lot. Okay, does pull probe and OLS still estimate the average partial effects? Well, yes, they did, right? And we discussed that. Now for the $1 million question, what about the random effects? Can that account for heterogeneity and uncover the true parameters? So I was just, scaling with these parameters. I didn't know what the parameter was, right? Because it's not estimated it. So can we estimate that with a pull probe? Let's try to do the random effects probe. So can we? Yes, can we do it with the random effects probe? Yes, we can. That's like what Obama says. We have heterogeneity. Alpha is not 0, and we're estimating that parameter to be very close to 1. Okay, so our quadrature method works. Okay, it's really we're doing heavy duty econometrics now, right? 1,000 observation, 10 time periods. We got delta right. We got sigma right. With our random effects being present, so we have counted for heterogeneity. Okay, the average partial effects, what are they? Well, they are similar to what we got before, right? So if we were to estimate this one here instead of with the random effects probe, we would that say I'm not sure this is going to work. So let's be careful. So what do? We do the pooled. Let's hope the things are coming in the right order. Yeah. Okay. Estimating the same sample, we got the same parameters, right? Even though coefficients are very different. So we got the same average partial effects. Okay. So that's very nice. And so now we're ready to move on to the next topic, to talk about dynamic models. And actually, that is this model that we're simulating data from. It is actually allowing for us to have a generate dynamics. Say if we put rho, say equal to 1, well, you're gonna get persistence in the in that variable due to state dependence. And we're gonna look at that model. How do you estimate that parameter? Is it important to account for that heterogeneity? And for the initial conditions, that's a topic for the next lecture. I really look forward to that. It turns out to be extremely important to account for these two effects if you want to estimate dynamic models. So anyway, let's take a break and move on. Get ready to move on for the next video. Spend some time with the notebooks and have fun.